Hello, am I audible? Hello everyone, I am Himanshu. Until now we have discussed the problems about trusses and few general problem related to equilibrium and force and movement balance. So, we will now again extend these concepts to beams. So, in this tutorial, we will going to discuss or solve few problems related to beams. The beams problems are pretty much, not that difficult. I mean, they are easy and they are quite interesting as well. So earlier we have solved problems related to truss, and you found that in truss, basically we have considered the force along the truss, which is in the outward direction from the pin. So this could be a force on the truss or one of the member of the truss. But in beams, mostly we are interested in the transverse loading. So that's the main difference between beam and truss, that beam supports the transverse loading, and they are very integral component in engineering, and that's why it is really crucial to understand the basic concepts like how force are distributed in across the beam and so on. So here, one of the assumption that we will follow, which greatly simplify the calculation, is we usually consider all the calculation in 2D. That means we don't need to consider the width of the beam for now, at least in this course. So we will neglect this width of the beam, and therefore our analysis mostly restricted to a two-dimensional domain. So there are various types of beams which are usually found. For example, it is actually defined based on the how beams are hinged or attached to something. For example, we have a cantilever beam in which the end of the beam is fixed, and therefore there will be two normal reaction which react, R1 and R2, and there will be a one movement which will be there at the end, and there will be different kind of loading at the other side of the beam. For example, it could be a distributed loading, or it could be a point loading, or there could be a external movement or couple which is acting across the beam. Now then there will be a simply supported beam in which the beam is, just as the name suggests, it is supported at the two end. So it could be a roller joint at one end, or it could be a pin joint at one end. So if you have a roller joint at one end, we know that there will be only one normal reaction. But if we have a pin joint at one end, then there will be a two normal reaction, or the two reaction forces, and there will be no movement in either of the case. Then there will be a overhung beam. It happened, this is a type of beam when it actually exceed the support system, and you can see this part of the beam is clearly hanging. It's not supported by anything else except this roller joint at the end, and there could be a distribution of forces across this beam also. It could be any distribution of forces, or it could be a point forces. So in all of these beams, we can see that this different kind of distribution of forces are actually the transfer forces, and therefore beam can able to support the transverse forces. And this is basically a difference between when we analyze the member uh, of a truss and here in the beam. So this is the basic difference in the member, truss member, or in the beam. So we will start with a very basic simple example problem where we have only a point force, and we will see how to solve such type of questions. And then eventually we will move to different kinds of question which is varying with difficulty and the concept. So first we will consider an example problem where we consider the simply supported beam. So here it is A, this is B, and this is the external force which is acting P. Let's say this is my AY and this is BY. This is A and this is B. So whenever we have given the beam problem, our first step is to analyze the reaction forces. So first we need to find for AY and BY. So for that we already know we have to take the movement across at any point, it could be B or A, and then we can actually find AY or BY. So if I take a movement about B such that my clockwise is positive and anti-clockwise movement is negative, I will have AY, and let's say this the total length is L. So this will be AYL, and it can, you can see it is actually moving in the clockwise, rotating in a clockwise direction along point B. And then we have minus PB equals 0. So AY equals to PB divided by L. So this is my reaction force AY. Now our objective is to determine the forces across this beam, which means that what is the forces at these points and movement across these points. So this is the usual objective in the beam problems. So we will consider a section of beam here, and we will cut in half. Let's say I cut in this portion because I am interesting what is the force here at this point of the beam, forces and movement. So I will zoom it out. So this is AY, this is A, and this is the cut portion, and here I will denote forces and movements. So this is my movement and this is my shear force which is acting on this arbitrary point which I am interested in, and this is at distance x. You can also consider another half of the beam. So if you consider another half, it will be look like this. So this is B, this is P, this is X, and this is the same point, but you are now considering the another half, and this is the same point, and here you define shear force and movement. So you can actually consider any of this part and then do the force balance analysis. So let us consider this part, and when we consider this part, you can see that your objective is to find the force V and M. So if I do the force balance analysis in y direction and say that the beam is in equilibrium, which makes the summation of force equals to 0, then I will have AY minus V equals 0, and AY we already found it's PB divided by L. So this will give V equals PB divided by L. And that is quite obvious result because we see that after this reaction force AY, there is no other force across the beam. So at each point, the force will be the same. So beam is experiencing same force at each of the point. So is experiencing same transverse force loading at each point. So it remain constant PB divided by L. Similarly, if we find the movement at this point, so if I take the movement at the same point here, I will have AY. And remember that the clockwise is positive. So I am following the same definition. So AY X, because it is X distance from the random point, minus M equals 0. So it will be PBX L minus M equals 0. So this will give me M equals PBX by L. So this is my movement, and you can see that my movement is increasing. So earlier this shear force, the shear force we actually find out, we observe that it is constant across each point of this beam, because as you increasing x, this equation is independent of x. So this is constant as we increasing x. But the movement is not constant as you increasing x. So movement, this bending moment is increasing. So as you are going left to right, your bending moment is increasing. For example, if you want to plot the bending moment, let's say your bending moment is minimum here, it is keep increasing even though there is no force acting here other than the force AY. Your bending moment is increasing because this x is increasing. So as this s increases, the bending moment also increases because this bending moment directly proportional to x. And therefore you will have an increment in the magnitude. It could be either this if your bending moment is negative, or it could be also this if it is positive. But the shear force is constant, which means the, if the shear force here is here having this magnitude, which is PB by L, it will always remain constant until it reaches this point where you have the external force loading. Until then it will be remain constant. So this is how you solve the uh, beams problem. You actually solve for different forces at different location on the beam. So first you actually need to calculate the reaction force, because this is very important in the beam problem. Once you define the reaction force, you could also calculate the By, but for since we have considered only the left part of the beam, we are only interested in Ay. Then we decided to take some arbitrary point here, and we decided to find the force and movement at this point. And we found that the shear forces, so we actually cut the beam at this point. We divided the beam into two part when we consider the left hand side of the beam, and we denote the shear force and bending moment at that point, and we do the force balance and moment balance analysis. So when we do the moment balance analysis, we found that the force is constant, which is quite obvious answer. But when we do the moment balance analysis, we found that the moment depends on x. So as we increasing x, as we going from left to right direction, the bending moment experienced by the beam is also increasing, and that is slowly due to this x. So we also can find the force at some other location as well. Let's say I decided to find the force here, another random location somewhere here. So again we will cut the beam into two part. So in that case,
Himanshu, just a
yeah,
general question. Is it
yeah,
okay?
yeah,
What is the difference between torque and a movement?
they are the same quantities. So
They're the same?
Yeah, they are the same. So movement can be, so movement is a vector, right? So what happens that movement have different components. For example, let's say, and this is my some beam. Okay, so what happens? If you have a movement and you are talking about three-dimensional system, then it can actually rotate about this z-axis, it can rotate about y-axis, and it can also rotate about x-axis. So basically, the torque is acted when the movement is trying to twist this body. So you have this body and it is actually trying to twist this body. So basically, if the movement is acting along the x-axis, that is what we call torque, because the torque always try to rotate or twist the body along its major axis. And when the movement is acting in the other direction, let's say in z direction or in the y direction, then it's usually referred to as a bending moment or simply as a movement. So both torque, bending moment, they all are the movements, they are just different components of movements.
Okay, thank you. Also, just a very like
Yeah,
according to your problem, right? That P point from the A distance.
yeah,
Usually, when a force P is acting at a point A, the more the distance, the more the moment, right?
yeah, yeah,
Uh,
yeah.
so in this case, the moment is maximum at where the force is. Like
uh, that
because
we have yeah,
yeah,
that we have to solve and check. So we
so
will solve we will
it can be
solve
different also.
Yeah, it can be different as well. I mean, it depends on the problem. I mean, it's not necessary that the bending moment should be maximum where the force is acting. It could be
Hmm.
different, and we will see in one of the problem where we will make a bending moment and shear force diagram. We will see how the moment is varying.
Okay,
Yeah,
thank you.
yeah. So now let's consider I choose another random point here, and it has a distance of x again. So let me make a diagram. So I'm considering again left side part of the beam ay. This is my p. This is some random point which has distance x. This is a. And again we will do the force balance analysis to see what is the force at this point x. So my force in the vertical direction is 0, the equilibrium, and it will be ay minus p plus v equals 0. So ay is pb by L minus p plus v equals 0. So it will come out to be, so this is my v. And if I do the moment balance analysis at this point, so I will have ay x, which is, so ay have a clockwise rotation along this point, so it's positive, and p will have anti-clockwise, so it will be p, and the perpendicular distance is x minus a minus m equals 0. So it is pb by l x minus px plus pa equals to m. So m will be p bx divided by L minus x plus a. So this will be the movement across this point. Now you can actually keep changing this x from x equals 0 to x equals L, and you can actually see the variation of the movement from this beam from x equal to 0, and you can see this m varies as linear. I mean, m varies m actually depend linearly on x. So the plot you will have here will be linear. It should be either this or it should be either this. It should not be like this curvy kind of a plot, because m actually proportional to x, and if it is n proportional to x square or x to the power n, then you will have a curve variation of bending moment uh, across the L. And for the shear force, again you will get a constant, which means that, so earlier we got the shear force at this point, which was Pb by L. So it was a constant like this until this point. It was Pb by L, and at another arbitrary point here, we will get another constant shear force, which is minus Pb by L plus P. So it will be again a constant but at different location, like that. So it will be keep constant until P. So if you join this, you will get this shear force loading diagram something like this, where it is constant. So basically, if you have a point load, it can give you some discontinuity in the shear force diagram. And if you don't have any force between the reaction force and point force, your shear force will be constant. But for the bending moment, it is not a constant but varies linearly. It is varying linearly till here, and after there is a change. And you can see when you keep plugging x, when you keep changing the value of x in the expression, you will more clearly get how it is changing. So it could be like this. So this is just a representative. So this is how we solve for bending moment and shear force at different location of this beam. So let's try to solve problems here. So we will start with a similar kind of a problem. So this is the problem. So we have a simply supported beam and we need to find the shear force bending moment at point B and at point C. So B is just intermediate left of the 6 kilonewton force, and C is just intermediate right of the 6 kilonewton force. So basically in this problem we are trying to understand that what happens just before left side of this point force, and when we analyze force at just intermediate right side of the point force, how the shear force or bending moment changes. And some idea we already have because of this example we have solved. We know that the shear force is constant, and when it experiences the external point loading, it changing in a discontinuous way, whereas for the movement it always change linearly with respect to distance. And once it experiences the point force, the bending moment changes, but then this changes is also a linear, it just change in the magnitude. So there will be a discontinuity as well, but after that again the change will be linear, because the bending moment again depends on x, whereas the shear force remain constant throughout except at this discontinuity where we experience the point force. So in this example also, based on the previous discussion, we can expect that my shear force will be constant here, and since it is experiencing a point force, there will be discontinuity, and after this point force again the shear force become constant. Something sort of behavior we will get here as well. And for the bending moment again, it should increasing in the linear fashion, and after it experiences the external loading, it will change to some value, and after it change there will be again a linear variation because we have only a point loading. In case we have given the distributed load, then the shear force and bending moment will get changed. So bending moment mostly become quadratic, which means my m now are proportional to x square or x to the power 3 and so on. It depends on the type of loading. So in that case my bending moment now change like this in a curvy manner like this. So that we will see it. So it's a similar problem like we have discussed above. So as usual, our first objective is to determine the normal reaction. So first we will make a free body diagram. This is AY, this is D, and there is a couple 9 kilonewton meter. Okay, let me make this straight. This is 6 kilonewton. This is B and this is C. Right. So if I take the moment at point D and assuming that clockwise is positive and negative is anti-clockwise movement, then I will have AY multiplied by 9 minus 6 multiplied by 6 equals 0, and this 9 also. So there is a moment which is acting at point D, so we have to consider that, and this is minus 9 because this is anti-clockwise. So 9 AY equals 36 plus 9 equals 45. So AY we will have 5 kilonewton. And this is my AY. Then in order to find the quantities at these 2 points, let us cut this beam first across B. So we will first cut this beam across B. So we will have AY. This is at B, which is 3 meter from A. Let me define here the forces. So this is NB, VB, MB. Right, so our objective is to calculate these forces. So when we do the force balance analysis in the y direction, we will have AY minus VB equals 0. So VB will be AY, which is 5 kilonewton. So force at VB at point B is 5 kilonewton. And if I take the moment along point B, I will have AY multiply 3 following this sign convention. Minus MB equals 0. So this will be MB A3AY, which is 15 kilonewton meter. So moment at point B is 15 kilonewton meter and shear force at the same point is 5 kilonewton. Now we will make a cut at point C, just intermediate right side of this 6 kilonewton force. So it's 3 meter So 6 kilonewton, and we have VC, NC, and the moment NC. So again, we will do the force balance analysis. Equating force in the y direction equals to 0. So we will have AY minus 6 minus VC equals 0. So AY is 5 minus 6 minus VC. I can take it to the right side. So this will give me VC equals minus 1 kilonewton. And to find the moment, we do the moment balance at point C. So AY having the clockwise sense around C, and yeah, so yeah, moment at point C is same. It's 15 kilonewton meter. So you can see that just intermediate right side of this 6 kilonewton force, the moment is same. So moment at point B is same 15, and at C also it's same 16. So this point B and C are the adjacent point from this force. One is the left hand side of this force and another is the right hand side of the force. So there will be no change in the movement due to this force. Of course, if you go little farther than here, the movement will get changed, because when you cut the beam here, let's say, then you need to consider the movement due to this force. So there will be a change in the movement when you consider far from this 6 kilonewton force here, here, or here, but just adjacent to the 6 kilonewton force, there will be no change in the movement, which means there will be no discontinuity. So like we have did here, we were wrong. There will be no discontinuity in the movement, there will be a discontinuity in the force. So the shear force, we found that it was 5 kilonewton just left hand side of this external force, and it is minus 1 kilonewton after the in the right hand side of this force. So this point load actually make the shear force discontinuous. So if I make the shear force diagram, it will be 5 kilonewton. So this is the location where my external force is acting. So this is 5 kilonewton force, and after this, where the point force is acting here, there will be a discontinuity in this force, and it will be now minus 1 kilonewton. But there will be no sudden change or discontinuity in the movement. So if I make the bending moment diagram, even though I don't have space here, let me try to make here also. If I make here the bending moment diagram, so you can see that at MB it is 15 kilonewton meter, and we discussed previously that bending moment should vary linearly because M is proportional to X. So it should vary linearly, somewhat like this. So here it is 15, and here also it is 15. There is no sudden drop or discontinuity in the movement due to this point force. And after that, there might be some change in the movement here, and it will change like this. We don't know about this change because we have not found movement at the right hand side of this force, but we will look in the subsequent question that how the bending moment will change when it experiencing the distribution force or the point forces. But as of now, we are not concerned how it is changing. The only thing we got to know from our calculation is that there will be no discontinuous change, I mean sudden drop in the moment, just when you introduce this 6 kilonewton force. So here in this question, we actually consider this left hand side of the beam, but if you consider the right hand side of the beam, you will get the same answer.
Just one question, like
Yeah,
here the 9 kilonewton meter what they have given, right? That will be used to find the initial reactions of A and D, right? So that it will be
yeah,
used there. But
yeah,
in the bending moment or shear, it will not be used. But even in the bending moment while we are using it, it will never be used, right? If we keep cutting from the left side from E,
yeah.
that
If
will never come into the picture at all.
Yeah, yeah, yeah. If you keep cutting from the left hand side, it will never come into a picture. But
Okay,
even if you do the analysis from the right hand side,
it will
then
come.
you have to consider this 9 kilonewton force, and the answer should be the same. So we can actually try this.
No, 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 no. I know, but I'm
Okay,
just asking. So
okay,
basically, I think the reaction force is what we found out.
yeah,
I think that will already include that
yeah,
component.
yeah. Yeah. It
So
will include.
that is why it's happening
Hmm.
in that.
Yeah,
That's why
yeah.
it matches. Like from the
Hmm.
left, from the right, if we take the cut, again it's the same answer
Yes, yes.
eventually.
Yeah, yeah.
Where, okay,
Yeah.
thank you.
Okay. So now let's move to the next question. Yeah, so in this question, we have modeled the ladder rung as a simply supported beam and assume that the 750 Newton load exerted by the person's shoe is uniformly distributed. Okay, and determine the internal forces and movement at point A. So here we have a simply supported beam, and this is my point A, where we have a force 750 Newton. So it is said that we have to model this force which is exerted by the shoe as a uniformly distributed load. But you can see the force is given in newtons. So even if we make the uniformly distributed load here, so this is how the shoe is actually distributing the force across point A, and this is 100 millimeter.
That
How?
is not
Yeah.
like even if we visualize, it's not pin supported, right? It looks like a
No, but this is given in Newton, 750 Newton. So this
no, no.
750
I'm
Newton is
just
the equivalent force of this uniformly distributed load. So,
that is okay. I'm talking about the supports. The supports
ha,
look like a
supports.
fixed thing, like
Yeah,
like
for
that.
this you can have x direction and also you can have a movement.
Mm,
But anyway, if you find the reaction forces, you will not find any forces. You will find that this horizontal force will be zero because there are no horizontal forces inside the beam.
mm. So if the leg was like in a little tilted angle, this whole problem would be a indeterminate kind of thing, right? Because six unknowns would be there.
You are saying that if I
If
make this whole
was
beam,
if that force was in a tilted angle, right now since the 750 Newton whatever is acting vertically downward proper, right? So there is no reaction on the horizontal side at all.
yeah,
But
yes,
if it
yes,
was tilted, even if the leg was
yes,
even,
yes.
so that would make it indeterminate, right? In this scenario, we couldn't solve it after. Like we only have three equations: moment fx, fy, and sigma moment zero equal to zero. So in that case, we wouldn't be able to solve it, right? If that was the
Hmm.
case.
I mean, we can find the reaction forces still because for the reaction forces, you have. Yeah, that is yeah, yeah. So it is actually very difficult to solve because you have the reaction forces here and here,
Yes.
which are quite different. And yes, I mean from the single equation you cannot able to find the horizontal reaction.
So through statics, like through the equations of statics, we cannot at least
Yeah, yeah,
give it.
yeah,
Thank you.
yeah. So this will be 0.25 meter, and this is zero point 0.2 meter from here, and overall it's 0.375 meter. So we can actually find this W, which will be, so my force is W x, my W will be F by x, and F is 750, x is, let's say, this 100 millimeters, so it was zero point 0.1, so it is 7500 kilonewton per meter. Okay, so now we need to find the reaction forces. So let's say this is B and this is point C. So if I take a moment along point C and equate it to 0, I will have B 0.375 minus 750, and then we require this distance. So it will be 0.375 minus 0.25 equals to 0. So here I will have 0.375 B equals 750 0.125, this is equals to 93.75, and B will be 250 Newton. It should be Newton. This is also Newton. So since we need to find the shear force and then bending moment at point A, we can actually cut across here at point A. So then our beam will look like, the free body diagram of beam will be, this is B, and this is the distributed load I have. This is zero point 0.2, and this is 0.25. So this end will be balanced by this reaction force here. A. So now since this is the uniformly distributed load, we need to find its equivalent point load. So earlier the equivalent point load was 750 here, and that was the equivalent point load of this entire uniformly distributed load. But now we have considered half of it. So its equivalent point load will be different because we have considered only this part of the uniformly distributed load. So here the W was 7500 Newton, and this distance is uh, 50 millimeter, which is 0.05. So my point load will be 375. And this, and for this uniformly distributed load, my point load always be in the center or at the distance of x by 2. X is the distance from any of the h. So this is actually 375 Newton. So earlier it was 750 for the entire 100 millimeter uniformly distributed load, but for the 50 millimeter distributed load, its equivalent point load is 375, and it is acting at the midpoint of 0.05, which is the centroid of this shaded area, red color area. So it will be at a distance. So the distance is from point B is 0.225 meter to this point load. So this distance we require to find out the moment. So if I do the force balance analysis in the y direction and equate it to 0, I will have simply B minus 375 minus VA equals to 0. So my VA will be B, which is 250 minus 375. So VA will be minus 125 Newton. So let it be like minus only. We will consider minus. So I am not changing the sign. I will consider minus as of now. So if I do the moment balance analysis at point A equal to 0, I will have a movement due to reaction force B in a clockwise sense, and clockwise is positive. So it is B 0.25. Then it is due to 375 Newton force, and it is anti-clockwise, so 375, and it has a distance of this blue color line is actually the perpendicular distance, and this distance is 0.25 minus 0.225, and then movement at A, which is MA equals 0. So my MA equals B, which is 250 multiplied by 0.25 minus 375, 0.25 minus 0.225. This is 62.5 minus 9.375. MA will be 53.125 Newton meter. So this will be my movement, and this will be my shear force at this point A. So any issue in this question? So this question was similar to the previous one because we need to find the force and movement at particular point A here. The only difference here was we have considered the force, shear force, as and model this force as a uniformly distributed force, and we need to find the force and movement at a point A which is in between of this uniformly distributed force. So we cut the beam such that we cut this uniformly distributed force in half, and when we consider left hand side of this beam, we only consider half of this uniformly distributed force. It actually changed the equivalent point load, which is now the 375 Newton. But we to find the moment we need this force per loading W, which we found 7500, because the 7500 will give us the modified equivalent point load, which depends on the distance at which it is distributed forces acting. So then we once we found out the equivalent point load, we actually repeat the analysis by doing the force and moment balance calculation. So when we do the force balance, we got the force at point A, which is minus 125 Newton. So basically our assumed direction was incorrect. It should be in the upside direction. And when we do the moment balance, we found the moment is 53.125 Newton. So any doubt here?
No.
Yeah. So we can move to the next question. So in the next question, we have a uniformly not uniformly, it's a distributed load which is varying, which is actually a maximum at one end and almost zero at another end. So, and we need to determine the forces, shear force, and moment at point C. So, as usual, we will find the reaction forces. So, to find the reaction forces, we need to calculate the equivalent load. So, if the distributed force is uniform, its equivalent load will always act in the middle or at a distance x by 2. So x is the distance from this side or any of the side. So this is my x by 2 and this is x by 2. Because this is a centroid that we have discussed at the end of last class, and this is the equivalent load for this uniformly distributed load. But if we have a distributed load like this, then what is the centroid of it? We actually found the centroid of triangle in the last class, and the centroid is from the base, it is 2x by 3, and from apex it is x divided by 3. So this is the equivalent load of this triangle looking varying load here, and it is at the distance of x by 3 from apex and 2x by 3 from the base. So if we want to find the, and also yeah, you,
It's the other way around, right? X by 3 from the base distance. It's acting X by 3 from the base.
yeah, this distance is larger, yeah, sorry, it is 2x by 3 and this is x by 3, yeah, sorry, yes. So it is x by 3 from the base and 2x by 3 from the apex. And to find the equivalent load, we need to calculate this area. So here the area is, so this distance is W, which is basically a force per unit length, and this is the distance where the force is acting. So its area is actually equals to the equivalent load. And similarly for this, so when we calculate the area of this triangle, we will get the equivalent load. So it is this distance, which is W, and this total length of this triangle, which is L. So my equivalent point load will be WL by 2. If we consider this L, then it will be WL. So having used this concept, we can find the equivalent load here. So it will be somewhere here, and here the distance will be, so this will be 2 meter and this will be uh, 4 meter. And the magnitude will be area of this triangle, which is 4 multiplied by 6 divided by 2. So this will be 12 kilonewton. So this equivalent load will be 12 kilonewton. So now we have an equivalent load. Now we can easily find the reaction forces. So here I'm again not drawing the reaction force in the X because it's nothing, it's zero. This is 12 kilonewton. A, B. So if I take the moment at point B, indicate it to 0, again the clockwise positive and the negative uh, is the anti-clockwise movement. So I will have AY 6 minus 12 multiplied by 4 equals 0. So AY will be 12 into 4 by 6. So it is 8 kilonewton. So AY is 8 kilonewton, and so now we need to find the force at point C. So we will make a cut along point C. Let's say this is my C. So my, and then I will consider right hand side of this beam, because if I consider the right hand side I will still have this triangular loading. If I consider left hand side, then I will not get exactly a triangle, I will get some trapezoidal kind of a shape, and we can actually solve the trapezoidal kind of shape. For example, if we have a left hand side of the beam, this is point C where we make a cut, we will have this kind of a loading. So what we can do, that we can split this loading into two parts. You can see the upper part will be a triangle, and the lower part of this loading will act like a rectangle. So here we consider two kind of a loading. So it will have a point equivalent load associated with the rectangle at the central of this beam. Then there will be a equivalent load associated with this triangle, and it will be x by 3 from the base. So here we are basically talking about two equivalent point loading, P1 and P2. And yeah, this P1 and P2. So instead, if we choose this right side of the portion, then we will get a triangle kind of a loading. And our analysis will become quite easy, because here we need to consider only one equivalent point force instead of two in the left hand side. So now we need to calculate By also, right? And the By, if I do the force balance analysis, so my Ay plus By equals to 12. So my By will be 12 minus Ay, which is 12 minus 8. So my By will be 4 kilonewton force. So still in this problem you can choose left hand side or right hand side. Left hand side is a little bit more involved because you have to deal with two equivalent point forces. But when you consider right hand side, you will have only one equivalent point forces. So I'm considering the right hand side. So this is By, and this is my shear force at point C. Right. So again, we have given the 4 kilonewton per meter, which is the highest loading at this point. And you can see it is keep changing. It is actually become zero here. And at point C, we don't know what is W, because W at point A is 4 kilonewton per meter, but W at C is not known to us. But since this is the loading has a shape of right angle triangle, we can use the property of triangle. So basically, we can use the ratio of triangle. So we can say that, let's say this is my W1 and this is my overall length, which is L1. Similarly, this is my W2 and this is my L2. So from the ratio of triangle, I can say that W1 by L1 equals to W2 by L2. Okay, and this is actually valid at any point on this triangle because it is linearly vary. So I can use this linear relation which is obeys for the right angle triangle. So W1 is the loading at the end and L1 is the total distance from that loading to the end of the beam. And this ratio should be equal to W2, which is the loading at C, and L2 is the distance from C to the same distance B. So W1 by L1 equal to W2 by L2. So our objective here is to find the W2, which is the loading at C. So W2 equals W1 multiplied by L2 divided by L1. So W1 we know it is 4 kilonewton per meter and L2 is 3 meters. So this point C is 3 meter from B, and L1 the total length, which is the length from B to the force where W1 is acting, 4 kilonewton, which is point A, is 6 meter. So my W2 will be 2 kilonewton per meter. So this is 2 kilonewton per meter. So now we can find the equivalent point load and we can also find the distance. So here this is 3 meter and its equivalent point load is somewhere here, which is 1 meter here and 2 meter here. And my equivalent point loading is actually WL2 by W2 L2 by 2. So W2 is 2, L2 is 3, so it is 3 kilonewton. So this is actually 3 kilonewton. So earlier my equivalent point load was 12 kilonewton and it is very much higher because W1 is higher and also L1 is higher. Due to this both reason, the equivalent point load was much higher. But now, since we have W2 and L2 both are much lower than the previous case, we got a little point equivalent load compared to the previous case. So now we do the force balance analysis in y direction. So I will have By minus 3 plus Vc equals 0. By is 4. So my Vc is minus 1 kilonewton, which means the direction of Vc should be downward.
The direction of VC, what you've taken right before the analysis, it's just a assumed direction, right?
It's a assumed direction here.
Yeah, because I think in the other problems, when you cut it from the left, the direction was taken downwards, right?
Yeah.
In this case, you've taken upwards. There is no logic as such to do that. It's just an assumed anyway.
Yeah.
You can take
Yeah.
anything.
Yeah. Just only thing we need, you need to make sure that if you consider the left hand side portion, Since now we have changed the direction of VC, we assumed upward direction, but we from the calculation we got downward direction. So in case you choose left hand side of the beam, then that should be opposite of this direction. This is the only thing we need to take care of. So we got this downward direction. So in case let's say we need to make calculation by considering left hand side portion, so in that case the VC should be upward direction.
The assumed
Ha,
direction should.
ha,
Okay.
so
So
it should,
basically, we can assume anything as long as it's opposite depending on the cuts, right? Like
yeah,
from
yeah,
the
yeah.
right. Okay. Okay.
You
Thank
can
you.
assume anything, but at the intersection, the direction should be opposite for left hand and right hand side diagram. That's the
Got
only
it.
thing.
Got it. Thank you.
So now what we need to do, yeah, movement at point C. So if yeah, if I take the movement at C, I mean overall movement, and it equates to zero, and assuming the clockwise positive and anti-clockwise negative, so we have by, and it is actually rotating in the anti-clockwise direction about C. So it's minus by multiply 3 positive 3 multiply 1 positive movement at C. So by is 4, so it's minus 12 plus 3 plus mhc. So mc will be 9 kilonewton meter. So this is the movement at point C, and this is the movement, shear force or the force at point C. So again, it was a similar problem, only the type of loading was changed. And even though the type of loading was changed, we saw that it is actually become quite a different question, because if you consider left hand side portion, you have to consider two equivalent point loading, and that was not the case with the previous diagram, because it is a uniformly distributed load. So even if you consider the left hand side portion, you will still have to deal with the same uniformly distributed load. So that is quite easy. But here both left and right hand side direction have different kind of uh, or different number of equivalent point loading, because in the case you have this trapezoidal kind of varying load, you can actually differentiate this in a triangle and a square, and it will have their own equivalent load. So we decided to go with the right hand side direction, and we found that okay, we don't know the force per unit length or the maximum force per unit length for this case. So we use a triangular law here. We use the triangular law because it is a right angle triangle, so we can use that law to find the uh, force per unit length across point C. And once we get that, we actually found the equivalent point loading and its distance from the base or the apex. Then as usual, we do the force and moment balance analysis that we have doing since 4 weeks, and we got the answers. So any doubt in this? Just
No, Iman.
okay. So now we change the force a bit more. So first we talk about uniformly distributed force, then the triangular kind of distribution force. Now our force varies non-linearly with x. So now it is varying at x to the power cube. And now we want to solve this question. So here we cannot use, a proper geometric formulas of area to find the equivalent load, or we cannot use unknown centroid distances. Like we know the centroid distances for circle, rectangle, triangle. We can't use this because it is non-trivial distribution of force. Now we will get. So this force is varying x to the power cube. Uh, so in this case, we will use a similar concept only. So again, as we discussed earlier, that our equivalent point load is just the area of distributed force. So earlier we got nice shape loadings like the loading in the form of rectangle or in triangle, and we already know the area of the distributed load. But now since the force is varying non-linearly in x, we can use the calculus to find the area. And in mathematics, we know that how to find the area under the curves. So if the curve is represented by w naught plus kx cube, the area under this curve will give the point equivalent load.
Could you just scroll to the right a little bit, like
Yeah,
is
yeah,
just a second.
yeah. So you can see we need to find the area, and in order to find the area, we need to calculate the area under the curve. So basically, we need to integrate this equation because the point force here can be given as W dx. So this is actually the area under the curve, and we need to integrate this expression W naught plus k x cube. So let's first find the value of k.
What is the W of x at point A? Like that axis is given as W of x. What does it mean?
Oh, W of x means, which means this W is actually a function of x. So as you go or changing the x, or as you go from left hand side to right hand side, this W should change because it is a function of x.
Okay,
So this is the W at
0.
x equals 0, and this is the W at x equals 8. That's all.
And W naught means W at 0. What does it mean?
W naught is some scalar constant that we have to find. So W
Okay.
naught and K we need to find.
Oh, okay, okay. So that is unknown still.
Yeah,
W naught.
yeah, yeah.
Thank
So that is what now I'm going to do. So we have this expression, and in order to find, since we need to get numeric answer, we need to find the magnitude or the magnitude of the reaction at support A. We will require to find W naught and A. So for this, we can use the boundary conditions basically. So what boundary condition means that I can consider this expression at this point because we know what is W at x equals 0. It is 1000 Newton per meter, and I also know W at x equals 8 meter, which is 2024 Newton per meter. And I can use this two equation to find two unknown because this, if I use these two conditions, then I can find these two unknowns. So if I use the first condition, so at x equals 0, my expression will be W equals W naught. Okay, and what is the W at x equals 0? It is 1000. So my W naught will be 1000 Newton per meter. And if I use the different condition, which is at x equals 8 meter, my W is 2024. So my W is 2024, and we already found W naught, which is 1000. So it is 1000 plus K, and this is 8 cube. So now from this expression we can calculate the K. So my K will be 2 Newton to the power m meter to the power 4. So now we have k, we have w naught. So our expression of w will be this 1000 plus 2x cube. So now in order to find the equivalent point load, which is actually the area under the curve, and area can be given by integral w dx. So it is this, basically integrating from 0 to 8 meter. So it is 1000 plus 2x cube dx. So it is 1000. I can split the integral. So it is 1000 multiplied by 8 plus 2. So it is 8000 plus 1 by 2, 8 to the power 4. So this will be this is my equivalent point loading. So my equivalent point loading I can write as 10.048 kilonewton, right? And in the previous class we actually learned how to find the centroid. So earlier we know the distance of uh, we know the centroid of some basic shapes like rectangle and triangle, but in the last class we've discussed that the centroid x bar can be found as x w dx divided by p. P is just the area. So we on the previous class we found that this quantity was area, but this area is equivalent to the point load, magnitude of the point load. So I'm writing this as P. So we will have, so let's first find this quantity, integral quantity. So it is, sorry, so let me define this as some P1. So this P1 is x.
Could you please
Ah,
repeat what the centroid part is? You've taken X bar something, right?
yeah, so this x bar is actually the distance of this equivalent point load. So this is my x bar from point A. So
Okay.
this equivalent point load should act uh, on the centroid of this kind of a curve. So for the general curve, if you have a general arbitrary shape of the body, the centroid, this is the expression of centroid. So you can find the centroid of any shape, any arbitrary shape by this integral of x w dx divided by the area.
X W dx divided by area. And okay.
So this we actually done last time. So let me go there.
That video will be available, right, for the
Yeah,
last.
yeah, it is. It is there. Yeah, I have uploaded in the YouTube actually.
Okay.
Yeah. So this was the explanation. So we were actually finding center of gravity, center of mass for the arbitrary case,
Okay.
and this was the
So this was last week, right? This
yeah
particular.
last week at the end of the class. So this was the expression I'm using. So this is the expression for the three-dimensional case, in which you have to consider the volume. For the two-dimensional case, instead volume you will have the area. So you will have integral of x dA divided by total area. And
I'll go through it
yeah,
eventually.
Yeah.
can continue with the regular thing.
Yeah, and this is the equation we have used just now. So we have divided this expression with a because of this a, and we are actually finding this x bar.
So there's a whole section which you thought only on this centroids and
Not the section. I just revised this concept at the end of the last class because before I want to move to the beam, I thought, okay, I should revise this
okay,
concept.
okay,
So
fine, no issues. I'll go through it after this.
yeah, yeah. So basically, this is my expression of centroid. So it will be uh, x multiplied by 1000 plus 2x cube dx. So in general, the expression of centroid can be given by this. So this is the general uh, expression of centroid, because I'm referring this as a centroid because this quantity x bar, which is referred to as a centroid, is depend only on the geometric properties like area, volume. So in two-dimensional case, this will be the area. In the three-dimensional case, this will be the volume. But if this quantity depends on mass and density, then the same x bar will give you the location of center of mass. If it is depending on the gravity, then same x bar will give you the location of center of gravity. So this is the expression I've used. So from this expression I can write x bar as x dA divided by A. So this dA is actually W dx here, and this A is actually the point equivalent force, which is P. So P1 will be 0 to 8, 1000x plus 2x4 dx. So here you will have 1000 x squared by 2, and here you will have x to the power 5.
Sorry to bother you.
Ha,
Just
ha, ha.
one clarification. Right now, the x bar is integration of x w dx. That's it, right? The area is not there right now, or is it still
No,
considered?
no, no, no. It's there only. I'm just trying to calculate numerator part only. Then whatever I will get, I will just divide it by p.
Got it.
Yeah. So I will. I'm actually trying to calculate this whole quantity x bar. Just, but first I'm actually calculating the numerator part. So it is 2 by 5. This is 8 to the power 5. So this will be 32,000. This will be 13107.2. So my centroid will be 45107.2 divided by P, which is 10048, which come out to be 4.489. So this is the distance of the point equivalent load, which is 4.489 meter from point A. So now this problem reduced to a simple point force problem on the cantilever beam. So if I make a, let's say I make here the free body diagram. Okay. So here it is AY, this is AX, there's a movement here MA, and this is a point load of 10.048 kilonewton and having a distance of 4.489 meter. And we need to calculate the reaction force AY, and it is easy. So if you do the force balance analysis, code it to 0, your AY should be equal to 10.048 kilonewton. And if you sum up the moment at point A and equate it to 0, then you will get MA minus 10.048 4.489 equals to 0. So MA will be 45.1 kilonewton. So this will be your bending moment at point A, and this will be your reaction force at point A, 10.048. So the only difference in this question was the loading of this distributed force was non-trivial. It was actually depend non-linearly on x. So what we did, we first using these boundary conditions, we actually first found these two unknowns. So if the unknown is more than 2, we cannot use, we need actually 3 boundary condition. So we have 2 boundary condition and we have 2 unknowns, so we can easily find 2 unknowns here. So in that case, we actually find K and W naught. Once we got K and W naught, we already know that the equivalent point force is actually the area under the curve. But since we have a non-trivial shape of this distribution force, we use the calculus to find the area under the curve, and we found it is actually around 10 kilonewton. Then we also need to find the location where this force is acting. And we know that that location is equivalent to the centroid of this area. So we need to find the centroid, and the general expression of centroid is given by this expression for the two-dimensional case. If you have 1D, then this area will be replaced by length, and if you have 3D, then this area dA and A will be replaced by volume. So using this expression, we can actually calculate the centroid. So it was little involved in mathematics, but it is easy to calculate because you know the expression formula to calculate the centroid. So it come out to be 4.489. So you find the location of this point equivalent load and the magnitude of this point equivalent load. So it actually simplified to very easy problem where you have a cantilever and you have only one point load is acting, and you just need to calculate the reaction force and the bending moment at this point, and that you can actually find very easily.
Could you just
Huh.
pause it at the end? Okay, just keep it here. Just
Yeah.
a second. Just checking my numbers. So, so, plus, 4, 4, 8. So negative here. Here. So usually you take bending moment clockwise positive. In this case, have you taken clockwise as negative?
uh, no, actually I have only two force, AY and 10 kilonewton force, and both are opposite in direction. So there will be one positive and one bending moment will be negative. I mean,
Yeah.
so this will be around clockwise. So this is clockwise, and this M is anti-clockwise. So one is negative and one is positive.
That I got it. Just the usual sign convention.
Oh,
What
okay,
you
okay, okay, okay. Yeah, yeah, yeah.
In this case, you've just taken it
Uh,
opposite, right?
but you can,
It's
yeah, if I follow the previous, then it will be negative
still
and it is
no, no,
positive.
no. I was just
Yeah, yeah.
checking. It was just habitually we're doing that. So this
Okay,
time,
okay, yeah,
4.485 is 45.1 kilometer. Okay, yeah,
yeah.
got it.
Yeah.
Kilonewton meter, right?
It's, oh, sorry, yeah, meter, kilonewton meter. So let's move to the next question. So in this question, we will try to make the shear force and bending moment diagram. Here I have written. So here we need to draw the shear force and bending moment diagram. So usually in this question, it is always desirable to make this diagram just below the beams. So you can easily able to show the location at each point. So for example, let's say this is the location for my shear force diagram. So I can actually mark this point as A. So here I will represent the shear force diagram at point A, and this will be my point B, and this will be my point C. So this is for SFD, and here I will make the bending moment diagram. This is A, this is B, and this is C. So in order to make shear force and bending moment diagram, we will use the same similar analysis. We just need to find the shear force and bending moment at maximum points. So we have to choose a multiple point and cut the beam in those point. So there will be a multiple analysis. So as of now, we have cut the beam once, and we have actually find the shear force and bending moment diagram at that point. But here we need to do a multiple times to get the idea how the shear force and bending moment diagram is varying, because from a single point it is very difficult to analyze how it is varying across the beam or over the entire beam. Remaining analysis will be the same. So as usually we will try to calculate the movement first. So for that we need the equivalent point loading here. So it will be uh, area of this distributed load. So it will be 10 kilonewton, and this will be 2.5 meter from here. This is also 2.5 meter. So if I take the moment across C at point C, and again uh, clockwise is positive and anti-clockwise movement is negative. So let me make a free body diagram first. A, this is C, so this is 2.5 and this is 5 meter. So AY will have a clockwise movement along point C, so AY multiply by 10, and minus 10 kilonewton will have an anti-clockwise movement. So and the distance is 5 plus 2.5, which is 7.5. And then there is a couple which is acting in the clockwise manner, so it's 50 plus 50 equals 0.
Can we call it a couple?
I mean, from this diagram we actually cannot, because for to call it couple we also need the direction of force, because couple always acting opposite. It is actually because of this opposite force, but here the overall force is zero, but there will be a net movement, and that net movement is actually a couple. So in
Yes.
order to call it couple, we actually need to see if the forces are actually in the opposite
It,
direction.
and
But
it is acting also, right?
yeah, yeah. So the thing is, this forces should act in the opposite direction, and the net resultant force should be zero. So this
Got
can be
it.
called as a couple, because you can see there's no force. I mean, if the net force is non-zero, then we have to represent in this beam. But since there is no force which is acting here, we assume that okay, the net force is zero, so we can call it couple.
Got it. So instead of the forces, this single thing is doing that job.
Yeah, yeah.
Thank you.
So this is 10 AI 75 plus 50 equals 0. So AY will be 25 by 10. So my AY will come out to be 2.5 kilonewton. And from the force vertical force balance analysis, I will have AY plus CY minus 10, which I can write equals to 10. So CY equals 10 minus AY, which will give me CY as 7.5 kilonewton. So now we have both reaction forces, and we need to make SFD and BMD diagram. So we have to decide where we have to cut the beam. So if I cut uh, somewhere between this uniformly distributed load, I can actually get the moment expression in terms of x that we have got in the at the beginning of the class. I can write moment in terms of x, and I can write the shear force in terms of x. So if I increase the x from A to B, I can see how my movement and force is varying from A to B. So if this happens if I cut somewhere between the UDL, I mean before point P. So this might be my first choice of cutting. Then secondly, I can cut after point B, because after point B I can cut anywhere. Like let's say I am cutting here. So then I can actually consider the role of the movement also. So this role of the movement is not there uh, in the SFD, but this movement will create discontinuity in the BMD, bending moment diagram. So just like we saw in the beginning of the class that the point load creates some discontinuity in SFD shear force, this couple or this movement will create a discontinuity in BMD. So another point we actually consider after this couple or after this point B to see how the bending moment changes. So we can have two point or the two cut, one between A and B and one between B and C. So if I cut, let's say somewhere here, here, so my free body diagram will be now this AY Let's say this is my shear force V, this is horizontal force N, and this is moment M, and I have a distance x. And the magnitude of this distributing loading is 2 kilonewton per meter. So its equivalent point force will be 2x at a distance of x by 2 here, and here also it should be x by 2. So if I do the force balance analysis in the vertical direction, sorry, I will have Ay minus 2x minus V1 equal to V equal to 0. So my V will be Ay, which is 2.5 minus 2x. So this is my expression of shear force, 2.5 minus 2x, which means that if you put x equals 0, your shear force will be 2.5. If you put x equals 1, your shear force will be 2.5 minus 2, which is 0.5. At x equals 2, your shear force will be 2.5 minus 4, and it will be uh, minus 1.5. And at x equals 5, that means at the end of this distributing load, it will be 2.5 minus 2 multiplied by 5, so it will be 2.5 minus 10, so it will be minus 7.5. So you can see that if you have a distributing load, uniform distributing load, your shear force varies linearly with x. Varies linearly with x. So this happens when you have UDL, uniformly distributed load. If you have point load, then shear force is constant. It is not varying, it will be constant, and this we have seen at the beginning of the class. For UDL, it is varying as proportional to as x. Whereas for point load, m is proportional to x, but here we will see that m will be proportional to x square. So this, from this expression, we can actually now able to find the shear force at every location, because you have to change x, that's all you have to do. So between A and B, you can able to find shear force at any location. So we got at x equals 0, the shear force is 2.5. So here it is this 2.5. Then at x equals 1, we got 0.5, which means, let's say this is my x equal 1 and it is somewhere here 0.5. So this will be like this, somewhere, something like, it will look like this. So this is the magnitude or SFD. So if we want to know when it is 0, if you want to know the location when your shear force is 0, what you need to do, you just substitute V equals 0. So if V equals 0, then it will be 0 equals 2.5 minus 2x. So it will be 2x equals 2.5. So x will be 2.5 divided by 2, which will be 1.25. So at x equals 1.25, your shear force is 0. This is at x equals 1.25, because you just need to put 0 here. So this is a master equation between point A and B. How your shear force is changing, this is your master equation, and from this equation you can find where your shear force is maximum in magnitude, where your shear force is 0, and all the variation you can see. So this is varying linearly with x. It's proportional to x, varying linearly with x. So this there will be a straight line.
How do we know what is the maximum value? Like,
You just keep changing x. So you can see here the maximum you got, magnitude you got when you consider at x equals 5. When you put x equals 5, you will get minus 7.5 kilonewton. So the magnitude, if you consider about the magnitude, you will get maximum magnitude of shear force and between A and B, and it is 7.5 kilonewton. You can actually do this. Let me check. Yeah, here you actually need to do by inspection, but
yeah,
for the bending moment, you can actually differentiate the expression of whatever the expression you will get. You will differentiate that expression and you can equate it to zero, because what happens, let's say if your bending moment have this kind of a shape, so when you differentiate and equate it to zero, basically what you are doing, you are saying that the slope here is zero. So basically this differentiation will give you the slope at different x, and if the slope is zero, like here the slope is zero, which means the bending moment at this point will be maximum, because the slope is here is zero. So in that case you can use this concept, because this is the expression of slope of the bending moment curve, and if it is zero, then the tangent line should be 180 degree, and when the slope is zero, at that point the bending moment is maximum.
got it. So you will be doing for this problem, right? That part is still there.
I'm going to calculate the bending moment now. So let's calculate the bending moment. So if I take the moment at the end of the beam and equate it to zero, then I will have the clockwise is positive. So ay x minus 2x multiplied by x by 2 minus m equals 0. So, yeah. So my m will be ay x minus 2 square by, yeah, 2 cancel, so it will be, m will be ay, which is 2.5 x minus x square. So you can see the variation of bending moment with x is not linear. It is quadratic. It is x square. So it's a non-linear, it's a quadratic. So it will not vary linearly like a straight line curve like this. It will actually vary like a parabola, like that, like this. And you can actually find, so at x equals 0, your bending moment is 0. And at x equals 1, our bending moment is 2.5 minus 1, and it is 1.5 kilonewton meter. At x equals 2, it will be 2.5 multiplied by 2 minus 4, so it is 5 minus 4, 1. At x equals 3, it will come out to the negative, which is minus 1.5 kilonewton meter. So if you keep doing this until x equals 5, you will have something like this. Like this you will have. Now in order to find where your bending moment is maximum, basically what you do, you have to draw tangent at each of this point in this curve, and if the tangent is 0, which means you are at the maxima of this curve. At maxima, the tangent or the slope of this curve will be 0 at the maxima, and that maxima will be the maximum BMD. So I'm just using the concept of calculus here. So basically trying to find out the maxima of this curve. So if I differentiate this expression and equate it to 0, I will have 2.5 minus 2x equals 0. 2.5 equals 2, so it will be 2.5 divided by 2, and this is 1.25. So at x 1.25, your bending moment magnitude will be large, so one can check that. So at m x equals 1.25, it is 2.5 multiplied by 1.25 minus 1.25 square. You will have 1.562 3.125, so you will get bending moment 1.563. So this is the maximum positive bending moment you can get here, 1.563. So this is 1.563, and this is at the location of x equals 1.25 meter. So as of now, this is my magnitude of bending moment. So as of now, we have calculated force, shear force and bending moment between A and B. Now we can actually make a cut here and see how the shear force and bending moment changes. So now we record another cut somewhere between B and C. Let's say here, oh sorry, let's say somewhere here. So my free body diagram will be and this is 2 kilometer 5. So this is 10. Equivalent point load is 10. This is 5 meter and the overall length is x. This is my shear force, let's say V2, N2, M2. So if I do the force balance analysis in the vertical direction Fy, put it to 0, I will have Ay minus 10 minus V2 equals 0. So V2 will be Ay minus 10. So Ay is 2.5 minus 10. So it is V2 is minus 7.5 kilonewton. So earlier we got V as a function of x, but now we got V constant, which is minus 7.5, which means that after this point, after it reaches 7.5, after it reaches minus 7.5, it will keep remain at the same value, minus 7.5. And this is quite obvious because after point B there is nothing, there is no force acting, no external force acting to change the B. So it is minus 7.5 only. Then we can calculate the bending moment M2. So clockwise is positive, so AY multiply X. So I'm writing AY as 2.5. 2.5x, and this distance is 2.5. So minus 10 x minus 2.5 and then I'm considering 50 kilonewton also, 50 kilonewton meter, and it's a positive, so it's plus 50 equals, sorry, minus m2 equals 0. So my m2 will be 2.5x minus 10x plus 25 plus 50, it will be 75 equals 0. So my m2 will be minus 7.5x plus 75 equals, sorry, this is not, yeah, minus 7.5x plus 75. Um, Correct, I think. Yeah. So this is the relation of bending moment between B and C. So you can see there's nothing, no force is there, but in the beginning of the class we saw that the bending moment keep changing. Bending moment still keep changing with respect to x because it is linearly depend on x. And we here also, since we don't have any force acting, we got bending moment which is linearly depending on x. So here we can found bending moment at different x location, like x equals 6, x equals 7, up to x equals 10. We can just keep finding the bending moment. And since it is linearly depend on x, there will be no curve or parabolic curve. It's a straight line from this point. If you so at x equals, let's say, 5, I will have minus 7.5 plus 75. So this is minus 37.5 plus 75. So this will be 70 37.5 kilonewton meter. So you can see that at x equals 5, you are getting 37.5. But in the shear force, you got same thing, because from this earlier analysis at x equals 5, you will get minus 7.5 shear force, and from the present analysis at x equals 5, you get same shear force, minus 7.5. But this is not the case with the bending moment because of this couple. So from the previous analysis, you will get the bending moment here, which was, uh, we have not calculated, but we got some negative bending moment here at x equals 5 meter. But from this present analysis, at the same location, we got another positive value of this, which is 37.5. So there is a discontinuity. From here, it actually directly jumped to 37.5. And this is because of this movement, because this movement is causing the jump or the discontinuity in the BMD, like the jump in the SFD we saw. So the point force can create a jump or discontinuity in the shear force diagram, and the couple or this movement can cause the jump in the bending moment diagram. So there is a jump to 37.5, and after that it is linearly varying, obeying this relation. So from this relation, you can see it is linearly varying. So this is minus 7.5x. So as you keep increasing x, you can see that the bending moment is linearly going down because of this minus 7.5x. So it will be keep linearly going down, and at x equals 10, you will see that it will become minus 75 plus 75. It will be 0. So at x equals 10, this will be 0. So this is your bending moment diagram at between B and C. And this jump you will not see. You will not see any jump if you don't have this movement. Even if you have a different kind of force which is acting just after the UDL, there will be no jump in the BMD. Only jump creating cause is this couple or the movement which is acting at B. So from that there will be a jump from this point to some 37.5, and then there is a linear decrement or the reduction in the bending moment according to this expression here. So just to recap, we need to find the SFD and BMD diagram for this problem. So we choose 2 point. One point we choose uh, between A and B, so we can see how the UDL, how the SFD, shear force and bending moment diagram is varying in UDL. Then we actually got a relation where the shear force is linearly varying on x, and the bending moment is quadratically varying with respect to x. And we actually find the shear force and bending moment diagram. We also saw that where this bending moment is highest in magnitude or the highest positive value. So for that we use the method in calculus where we actually try to find the slope 0 case, and there we actually differentiate this expression and equate it to 0. So we will actually find the location where the slope is 0, and that is actually the maximal positive value of bending moment. And then we repeat the analysis where we split the beam between B and C, and we saw that the shear force is constant once it reached to minus 7.5 from the earlier analysis. Our current analysis also says the same, that it is always remains at minus 7.5. But for the BMD, there is a huge jump because of this couple, and then there is a reduction till C, and that reduction can be defined by this expression minus 7.5x plus 75. So, any doubt in this question?
No, I want you.
Okay, then that's it for the today's class. So, next class we will try to solve friction problems.
Are those topics difficult compared to like these I knew, but friction dynamics and all those things, kinematics analytics, are those difficult or
So friction, I think mostly the question will be on the same concept. You have to use the equilibrium concept only, using the force and moment balance equation and equate it to 0. So whatever we are doing since first week, we will use the same thing in the friction. The dynamics is another concept. First in the dynamics we will cover kinematics, where we will talking only about the relation between acceleration, velocity, and displacement. So kinematics is all about the relation between all these three things in translation, and angular acceleration, angular velocity, and angular displacement for the rotational case. When we move
so?
to kinetics, we will deal with how the force influencing this parameter, or how this quantity is influencing the force.
So this, what do you say? The curriculum, whatever is set for this particular course itself, only that much is enough to understand those topics from beginning to end.
Yeah,
Like,
yeah, yeah. This is the standard curriculum. I mean,
right. So for the next 4 weeks or whatever weeks, those lectures are there. That should be enough, right? No need for extra.
no, no, no. I mean that should be very much enough. So next week we will be discussing on statics. Then from sixth week, I guess we will move to dynamics.
Okay, no problem. You will be there for all those topics also. You are the same
How I will be the
person.
same team. Yeah.
Yes. Thank you, man.
Thank you. Yeah.